Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Happy to have Ranjit Kumarasam visiting us. So Ranjit is currently a postdoc at MIT. He's also been at Technion in Maryland before that.
Nice.
And he's been working on multi-party computation, both sort of theory and practice, I think, and then also more recently on Bitcoin and building fair protocols on top of cryptocurrencies. And today he's going to talk about some of that work.
Thank you. Thank you for the introduction. Right, so I'm happy to be here. Today I'm going to be talking about privacy-preserving smart contracts. So let's start with, what are contracts? So contracts, the way I see it, these are basically, should I be worried about that? Or replace lamp. In 10 minutes, power will turn off. Okay. I'll try to finish the talk in 10 minutes. So the way I see contracts are basically formalization of human relationships, and contracts have been around for a really long time. So on the slide you can see contracts from the Sumerian civilization dating back to like 2600 BC. And this one is from the Tang dynasty dating back to like 700 AD. So they have been like all over the place for a long time. So any guesses as to what these contracts are for from the past? Any guesses?
Trade?
Yeah, trade of what? Food. So during those times, they were actually trading slaves. So it's like slaves for building and slaves for silk. So it's actually slave for silk and some food too. So yeah, so you got it partly right. So so mankind has progressed from like 2600 BC, and somewhere down the line we had phones, and phones became smarter, right? So why not contracts? So smart contracts, these are actually envisioned by Nick Szabo in his 1994 essay. And the deal with smart contracts is they try to automate contract management. Okay, so in his essay, he gives this example. It's a bit weird. I don't know where to stand. So he gives an example of this key which unlocks a car if and only if the monthly installment is paid on time. So you go and buy a car from a car dealer, and you promise to pay him like monthly installments, and he gives you a key, an electronic key, and this unlocks the car if and only if you pay the monthly installment. You pay the monthly installment, it unlocks the car. You don't pay it, it doesn't unlock. So with smart contracts, today everything is connected to the internet, right? So automating contract management is not per se super hard, right? So what is really smart about smart contracts is that they are self-enforcing. Self-enforcing in the sense that you don't need any kind of third-party intervention. So if something goes wrong, you don't have to go and sue someone and wait in a court of law for like 6 months for something to happen. So smart contracts are smart in the sense that they make like self-enforcing, they make contracts self-enforcing. So let's be a bit more precise about all the things that I'm talking about. So for this talk, you have to think of contracts as exchanges, okay? And exchanges of what? These are exchanges of like information for computation, information for information, information for money, computation for money, exchanges, some exchanges involving all of the above. So these are what I mean by contracts. And by smart contracts, I basically mean self-enforcing exchanges. So exchanges where you don't really need to rely on a third party to set things right. So what is difficult about smart contracts? Why is enforcing hard at all? So let's look at a very simple example of an information-to-information exchange. So here, Alice and Bob each have their own pieces of information. You could think of it as like some kind of confidential information. Maybe they're like spies trying to exchange some information. Or you can think of this as like a bill of sale for a car, and this is a bill of sale for a land, and they're just trying to exchange some property. And they're trying to exchange some legal documents. And now what you want at the end of the protocol is either the exchange happens successfully or it does not happen at all. It has to be like kind of atomic. And the way things can go wrong is, well, someone has to start the protocol, right? So maybe Alice starts the protocol, sends over a document, but then Bob becomes, Bob is malicious, and we are basically dealing with counterparty risks, right? So this is what can go wrong when you're talking about contracts where you want to enforce them without any kind of third party. But exchanges happen all the time in the real world. So how do people deal with these counterparty risks? Well, they actually use an escrow service, right? So there is some kind of a trusted angel out there who doesn't take either party's side, and then you just use the angel to perform the exchange, right? So here in particular, if you want the angel to perform the exchange, then in addition to the information, you also need to specify some conditions on the information. So this says conditions that the other person's information must satisfy. So this I'm going to capture by the Greek symbol phi. So the red symbol is actually going to check the red information for validity. So this could be like, you could think of the signature containing, the document containing the correct signatures from the correct authorities. Imagine it's like some bill of sale of a car. So it has to be a document signed by the DMV, attesting to like, hey, this is the car, this is the model, this is the make, this is the year, this is the owner, right? So you have these like conditions. So the red condition checks for the red information, the blue condition checks for the blue information. Then if you have an escrow, what you're going to do is, well, you're going to give the escrow both the information as well as the condition. The escrow is going to check whether the condition matches the information, and if everything is great, then it's just going to perform the exchange, right? So this is how things happen in practice. This is how we defeat counterparty risks in the real world today. But what does this mean for like smart contracts? For smart contracts, you want like self-enforcing exchanges. You don't want any third party, right? So in this solution, our escrow is really necessary. So maybe we can do something clever, not use the escrow, just use some kind of maybe cryptography or something else to beat to not require an escrow and just perform the exchange between Alice and Bob. But here we are faced with an impossible result from the 1980s due to Cleve. So he actually shows that such exchanges are impossible to enforce without a trusted party. So if you want an information-to-information exchange, then you need to involve a trusted party. That's what his impossible result shows. So where does this leave us with? Do you have a question? Okay. So where does this leave us with smart contracts? With smart contracts, we don't want to involve a third party. But then Cleve's impossible result says that you cannot enforce these exchanges without a third party. So what's going on here? So what am I going? Yeah.
So can't you do fair exchange, I guess, with no conditions, almost perfectly, like by doing one bit at a time?
Oh, so gradual. Yeah. So this kind of approach is called as gradual release. So maybe you encrypt the information, and then now you just want to exchange the keys, and you exchange the keys like bit by bit. So I send you one bit of the key, you send me one bit of the key, and we go so on and so forth. The problem with that approach is, well, what happens if maybe you're exchanging a 128-bit key, and you have exchanged up till the 70th bit, and then one person stops because he has a supercomputer in his backyard and he's able to brute force the remaining 58 bits. The other person, the honest party, well, so it's not clear what you do when, sometimes you might want the honest party to do an exponential amount of work, which is not reasonable. The other drawback is, well, for every exchange, you have to kind of like go back and forth 128 times, as many bits as you're trying to exchange. So there's a couple of drawbacks. And at the end, you'll still not be able to prove anything formally. You cannot beat this impossible result. So, yeah. So that's definitely something that you could use in practice, but it can, when the abort happens after the 70th bit, you start running into problems. Otherwise, it probably works. Right. So So how do we? What happens to smart contracts when you're faced with this Cleve's impossible result? So what am I going to talk about? So in some sense, I'm going to talk about like bypassing Cleve's impossible result. And here we are going to be, our intuition is going to be guided by this picture that I showed you before. So in today's world, there is exchange of information and money which happens all the time. You buy newspapers, right? So in some sense, information has some value. You can put some price tag on the information. Right? So you can equate information to have some value. Let's look at a different type of escrow. Not the information escrow that we saw before, but something like a money escrow. So we actually need to bring like money into the picture. So let's say the protocol starts in the following way. So this was the 10-minute thing. So let's bypass Cleve's impossibility result again. So just to give a little bit of wait, just a second. To give a little bit of context, so we were dealing with difficulties in self-enforcement of like information exchange, and there you had to deal with counterparty risks. And the way people today deal with counterparty risk is by using an escrow service. So here you have to specify these conditions which the other person's information has to satisfy. I'm just going back through the slides that I just finished before. So the escrow will check for the conditions, and if everything is good, then it's going to perform the exchange. So the escrow, the trusted angel in the middle, does not take any person's side. And the question is, well, this is not completely third-party free. You're still using a third party, so our escrow is really necessary. And here we looked at the impossibility result due to Cleve, which says that, well, these information-to-information exchanges are impossible to enforce without a trusted party, and this is like kind of bad news for smart contracts, because you want to get rid of third parties. Right? And so in this talk, I'm going to be looking at ways how we can bypass Cleve's impossibility result. And here our intuition is guided by this triangle that we saw from before. So information to money exchanges will happen all the time in the real world. So what this means is that information has some value. You can put like some price tag on the information. Right? So let's look at a different type of escrow, which is different from the information escrow that we saw earlier. Now it's a money escrow, and we bring money into the picture. And so can people see all the pictures? Okay, good. So in addition to the information and the conditions, they're also going to deposit some money with the escrow. Then they're going to start performing the exchange. And now if the exchange goes bad, then the money escrow is going to compensate the honest party. Right? So the information exchange is still going bad. So Bob gets both information. Alice does not get Bob's information, but Alice is compensated with some money. And well, you can set the safety deposit to equal to the value of this information. So this seems to be like a very reasonable notion in practice. Right? So the exchange still goes bad, but Alice gets some compensation. The honest party gets some compensation. But why is this any better? You're still using a trusted third party, so it's still not like smart contracts, right? So you're still relying on a third party. So why is this any better? So here my work shows that this escrow is impossible. It's possible to implement it in a setting where you have a self-enforcing information to money exchange. Right? So we can get rid of this trusted angel if you have self-enforcing information to money exchange. So let me go a bit more into what I mean by this self-enforcing information to money exchange. So I call these as claim or refund transactions. So you can think of like Alice making a transaction to Bob, and she specifies some information, some condition on the transaction, and also puts some money, right? And now Bob can claim this. When he claims this, so he gets the money, but then Alice gets the information. So it's kind of like an atomic swap of information and money. And of course, Bob could be malicious, and he does not perform the swap. In this case, the money just goes back to Alice. So either the swap happens or the swap does not happen. Okay, so this is what I mean by a self-enforcing information to money exchange, and we are going to implement this escrow where if the exchange of information does not happen properly, Alice gets compensated. We want to implement this using claim or refund transactions, which give, yes?
Does that involve a timeout? Is there like
Yeah, so it does involve a timeout. So Bob can claim this until a certain time. If it times out, then the money just gets refunded back to Alice. Right. So I'm talking about like a claim or refund transaction with the self-enforcing information to money exchange, but it still seems that, how do you enforce this thing? Maybe you still need a trusted party to ensure that this exchange happens atomically, right? So again, like, why is this any better? We switch from different escrows, but it's still not clear why it can be made self-enforcing. And the punchline here is this: is that Bitcoin implements this information to money exchange, this self-enforcing information to money exchange. This is possible to implement in Bitcoin. So this claim or refund transactions you can implement in Bitcoin. So if you're willing to take the leap of faith and assume that Bitcoin is real money, then Bitcoin makes this information to money exchange is very explicit, because in Bitcoin the money is tied to the public key, and if you have the knowledge of the secret key, then you own the money, right? So in some sense, if you have the information, which is the secret key, then you have the money, right? So there's some kind of an atomic exchange of information and money. So if you look at the blockchain, which is like the public list of transactions which are collected in Bitcoin in this data structure, so you can see that if Bob wants to spend the money that Alice sent to him, to Carol in TX3, then he basically has to produce a signature under his public key in order to do this. So the Bitcoin transactions are already like conditional. So you have to produce the signature in order to spend the money in the correct way. So even like basic transactions, they're already conditional. You need to know the secret key in order to produce a signature, and then you can spend the money. And Bitcoin transactions can be even more like general, in the sense that you can put in like any condition on top of this. So these are called as Bitcoin scripts. You can put like an additional script which checks not only for the public key, for the signature under the public key, but also checks for additional conditions, maybe conditions on the information, right? So but who is enforcing these conditions? You know, how is all this happening? Why can't Bob, you know, even if it does not have maybe someone else could claim this money that was spent to Bob. So why is this not allowed in Bitcoin? Here, you know, Bitcoin has this like novel mechanism in which it incentivizes Bitcoin miners to validate conditions and maintain the blockchain. So it's the miners who are doing this checking. So in other words, there's not like a single trusted escrow which is validating all these exchanges, but it's more like a network of miners who are validating the conditions and they're maintaining the blockchain. Yeah.
It seems like through Bitcoin something is happening which is theoretically impossible. Is it the case?
So you can think of it like that, or the other way to think of it is like, well, if you have a trusted third party, right, then you can beat all the impossibility results, right? Because the impossibility result basically says you need a trusted third party. You can think of Bitcoin as like a network of trusted parties. Network of parties, you trust like a majority of the computing power or whatever assumptions that Bitcoin needs to function and to maintain the blockchain. So you're relying on that assumption as opposed to just like one single point of failure or a trusted escrow. You're relying on a network of miners. So that is the way, that is the way to think about it. So you can think of it as like beating the impossibility result. I mean, in some way, Bitcoin gives you like a bank system, a currency system without any central bank, right? So in some sense, it's beating an impossibility result there. So it's kind of in the same vein, it's also beating an impossibility result here. So that's one way to think about it. But you know, but you might not be happy with this equation that Bitcoin is real money. Maybe American government will just ban Bitcoin tomorrow, right? So what am I talking about? Is the stuff that I'm going to tell, is it still going to be relevant? Well, the thing here is I'm going to be designing protocols based on this abstraction of this information to money exchange, based on like claim or refund transactions. So in my protocols, I'm just going to show you this like arrow notation and how you set things up so that you get your information to information exchange or like general smart contracts. But this arrow is going to hide a lot of these like implementation details on how you actually do it on Bitcoin. So in other words, this claim or refund transactions, this abstraction is definitely Bitcoin inspired, but it's Bitcoin independent. So in particular, you could have like this abstraction, this abstract claim or refund transaction being implemented by an information to money escrow. It becomes like a single party which implements this abstraction, and this could be like something like Bank of America or PayPal, anybody that deals with money. You know, these institutions typically deal also with information, your sensitive information. So they are like in a very good position to implement this information to money escrow. Or you could always go and use like a blockchain implementation. You know, either Bitcoin, Litecoin, Ethereum, any of your favorite altcoins. As long as they implement this claim or refund transactions, the protocols that I'm going to show are still going to remain secure, right? And the deal is we will still be worrying about like privacy and scalability issues, which makes sense no matter which implementation you work with. So to give more details, so if you're using an information to money escrow, and you're going to use this escrow to exchange this information, then what this means is that you're relying on a single point of failure. Right? So there's going to be like this, Bank of America server or something which is storing all the information, and well, we know that servers these days get hacked all the time. Right? So your information is going to leak. So through a data breach, your information is simply going to leak. Right? In the blockchain implementation, things become even much worse, because in order to check if this information satisfies this condition, you need to make the information public anyway. So this could be like sensitive information, because the miners are the ones who are checking this, whether this information checks out with the condition. So the miners need to know this information in order to check whether this condition is satisfied. So in the blockchain world, things become even worse with respect to privacy. Okay. When you look in terms of scalability, well, every time you use a claim or refund transaction, you're going to pay like some kind of a transaction fee to the information to money escrow. Let's say a Bank of America. And every time you use its services, you're going to pay some kind of transaction fee, and this transaction fee could depend upon the complexity of the condition that you're verifying. Right? Maybe this condition takes like 6 hours to verify. The bank is not just going to do it for free. It's going to charge you money proportional to the complexity of the verification. So in terms of scalability, you still need to work a bit hard. Right? In the blockchain world, things become even worse, because a large condition or a large piece of information actually is disastrous for the consensus mechanism in Bitcoin. So one thing is that, well, you need the miners to verify all this information with this condition, and if the information verification is going to take like hours, then the miners might as well just not perform the verification, right? So this is a problem where you're kind of like trusting a network of parties to carry out the verification, but they're not doing it at all, right? So then this totally undermines your contract. Also, when you have like large pieces of information floating around the network, then this is going to affect the consensus mechanism, because different parts of the network are seeing different pieces of the information. And it takes a longer time for them to synchronize with synchronize all the stuff in the blockchain. So no matter which implementation you choose, you still need like privacy preserving mechanisms, because the naive solutions just don't simply work. And you also need to minimize the on-chain complexity when it comes to like scalability. Right? And in this talk, I'm going to show you how to start with like these claim or refund transactions. And using a little bit of cryptography, we're going to design smart contracts which are both scalable as well as privacy preserving. So this is what I'm going to show you in the rest of the talk. So let's start with this like simple information to information exchange that we wanted to implement. So this is the stuff. The stuff on the left is what we want to implement. Right? So parties perform the exchange. If the exchange goes bad, then the honest party is getting compensated. Right? So this is what we want to implement. If the exchange doesn't go bad, then they exchange the information and everybody's happy. If the exchange goes bad, then the honest party gets compensated. So this is what we want to implement. We want to implement this using claim or refund transactions. So this is like the first thing that you would try. Well, Alice makes a claim or refund transaction to Bob, and Bob makes one to Alice. Right? So Alice deposits her money, and Bob deposits his money, and specifies the condition. And then when they want to exchange, so Bob's information satisfies this condition. He gets Alice's money, and vice versa. Right? So in this case, parties end up with each other's information and coins. So this is like kind of like a fair exchange. Nobody loses money. Nobody loses any information. Right? So this is one way to go about doing it. But of course, this is only when both parties are completely honest and they're following the protocol. Right? What happens if something like this happens? Let's see what happens if something goes wrong. So let's start with this case where Bob does not make a deposit. Right? So Alice makes a deposit, but Bob does not. So she makes a claim or refund transaction, but Bob does not. Because Bob does not make a transaction, Bob is obviously not losing any money, so he keeps his money. But then now Bob can go and claim Alice's money using her claim or refund transaction. And what happens here is that the honest party actually ends up losing money. Right? So Bob gets both the coins, Alice gets both the information, but this is an honest party. She started the protocol, putting some money, but then at the end of the protocol, she ends up losing money. So this is kind of like no good. This is not what we wanted on the left side. So we want an honest party to start the protocol with a full guarantee that it's not going to lose money, because it's behaving honestly, right? And we want to circumvent this problem. And if you look closely, the reason why there is a problem is because Bob needs just his information to satisfy the condition for Alice's claim or refund transaction. So we have to kind of change that. We don't want just Bob's information to let him get Alice's money. And the main idea here is, well, to use a double lock. So basically, Alice makes her claim or refund transaction, puts her deposit, but then she specifies that Bob has to supply information that satisfies both the red condition and the blue condition. So Bob has the red information, so he can satisfy the red condition, but he does not have the blue information, right? So he cannot directly take it. So let's run through an honest execution of the protocol. So how is this supposed to work? Well, first Alice is going to claim Bob's transaction. Right? So she satisfies the blue condition, releases the blue information, gets the money. Now Bob has both the red information and the blue information, so he can go and. Any questions?
So she'll only form that second thing if the first one. So that's actually in order at the top and the bottom.
Yeah. So this one is claimed first, and after that, so the deposits are made. This one is made first, then this one is made, then this one is claimed, and then this one is also claimed. Right? So what effectively has happened is that parties end up with each other's information as well as coins. Right? So this is, of course, again, it's an honest execution. Let's look at what happens when, let's say, Bob cheats, and the same attack as before. Let's say Bob does not make a deposit. Then again, Bob is not going to lose any money. I mean, he's actually not making a deposit, so he gets to keep his money. But then now he's not able to claim the top transaction because he does not have Alice's information. Alice's information would have been revealed only if she had claimed this. She does not claim it, so Bob does not have all the information to satisfy the top condition. So that thing just gets refunded after the timeout. Right? So what has happened here is that Alice does not lose money. They don't exchange the information either. But this is like an atomic swap. It's just that the exchange never happened. It's not an unfair exchange. So we are happy with this, as if like one party just never started the protocol. Right? So let's run through like one other cheating scenario where Bob cheats, but this time he does not claim the transaction. Last time he did not deposit. Now he makes a deposit, but he does not claim. Right? So here Alice again claims Bob's transaction, gets Bob's money, and now Bob does not claim. Bob has both the information, so he's just happy with it. He's not going to claim the top transaction. So what happens here is that after the timeout, Alice is going to get that money back. And effectively, what has happened here is that Bob has lost his deposit. Right? So Alice gets both the money, both the coins. Bob gets both the information. But this is okay because this is exactly what we saw, what is happening here on the left. Right? So this is, I've just run through only the examples where like Bob is corrupt, but this also works equally well when Alice is corrupt. Yeah. So it looks like we have implemented this information to information exchange using just claim or refund transactions. But the problem here is that there is kind of like no privacy here. Right? Because when you're exchanging, the claim or refund transactions are actually checking this information, and this information is going public on the blockchain for the whole world to see. Okay, so this is not good. So we solved the problem, kind of like the exchange problem we solved, but the privacy problem still remains. And well, how do you solve a privacy problem? You're going to use some kind of encryption, right? So you're going to encrypt the documents and maybe exchange the encrypted documents. But once you're encrypting, how do you check under the encryption? Right? So you need more than encryption. And here I'm going to say that we need something like privacy-preserving computations. So in the very general case, you can think of this as Alice having some input x and Bob having some input y, and they want to compute some function f of x, y on their inputs, but without revealing any extra information about their inputs. So you can think of this as like Alice has their information, Bob has his information. They want to check if the information is valid and maybe possibly encrypt it and do other things. But they want to do this in a way such that this computation itself should not leak their information right away. And so how do we get to do this? Let's start with a mental experiment where let's say they have access to an angel. Then things are very simple, right? You just submit your inputs, the angel computes the output and gives you back the result. So what Alice and Bob get at the end of the interaction is basically just their outputs. So in some sense, this gives you the best possible privacy, right? So this is the best that you can hope for. Alice and Bob, they just get the output of the computation. They don't get anything else, right? So can we implement this, right? So that is the thing. But here we are faced with the impossible result due to Cleve. It says that these types of angels, they are not possible to implement even for like simple exchanges. And you just want to exchange, they start with x, y, and you just want to swap it. x with y, it's not possible. So that's what Cleve's impossibility result says, right? So, well, maybe we cannot do this. Maybe Cleve's impossibility result has to do with like the fairness. And maybe if we relax fairness, things might be okay. So let's look at a different type of angel, where this angel is now going to give the output only to Bob. Okay, in the general case, it's only going to give the output to the corrupt party, and then the corrupt party can decide whether the angel should deliver the output to Alice. But it can decide maybe it should not deliver the output to Alice. So it's up to the corrupt party. Right? So the corrupt party can say deliver the output to Alice or not. Right? So you still get the best possible privacy, because what people get at the end of the interaction is basically only the output. They don't get any extra information about the other person's input. Like Alice does not learn anything more about y than just like the final output. And same thing with Bob as well. So you still have best possible privacy, but you don't have fairness. Right? And this maybe like many of you in the audience already know, this is basically the big result from the 1980s. This is secure computation, right? So you can implement angels via cryptography, and this you can do, and the parties are malicious, so on and so forth. It gives you the best possible privacy, but no fairness. Right? So armed with this tool, so let's look at how to make the information exchange that we saw before. How do we make it private? So, well, actually, so this is what it means implementing the angel. So you throw the angel out and then just replace it with a protocol. So let's look at private fair exchange. So earlier we saw that to do this exchange, these conditions checking this information publicly on the blockchain, and this was bad. Now we are going to use secure computation to make things better. And so obviously Alice and Bob are going to engage in a secure computation protocol. So let's specify what is the function that they're trying to compute. Like as we said before, it's going to involve some kind of an encryption, because you don't want to release the information out publicly, right? So what the secure computation is going to do is going to generate some fresh one-time encryption keys. So fresh encryption keys generated inside the secure computation protocol. Then the secure computation protocol is going to check whether this information satisfies this condition, this information satisfies this condition. It's going to perform all the checking inside the secure computation without revealing the information, and then it's going to encrypt this information using the one-time encryption keys. Then it's going to give out some output. Right? Note that how the output is what output is delivered to the party. So Bob basically gets Alice's information, but it's encrypted under Alice's key, and Alice has that key. Bob does not have that key. Right? Bob has the red key, but he does not have the blue key, and he has Alice's information encrypted with the blue key. Now note that secure computation does not give you fairness, so it's possible that only Bob got this output, Alice did not get this, but you can see that just these two does not give any information to Bob, because he only has Alice's encrypted information. He does not know how to decrypt it. Right? So now what we need to do is basically exchange the keys. This is kind of similar to the gradual release where you're like exchanging bit by bit. Now we want to exchange the keys, but again you have this problem, right? So if Alice sends over a key, then that's not good, because then we're running to the same problem as before. But this is basically some kind of an exchange like this. This is what we have to do. But here in this picture, we had these conditions phi, which were checking for the information. So we kind of need to have some conditions to check the keys. That's what we need. Right? Then you are in the same. Then you're in good shape. It's the same problem as before. But how do you generate this condition which checks the keys? Well, you can also do that inside the secure computation protocol, right? So you generate some authentication information for the keys. So this will be the red phi key which checks for the red key. The blue phi key checks for the blue key. And now you can also give this to the parties. Now you have set all the things up. They have to exchange the keys. They know the conditions the same as before. They were exchanging some information. They know the conditions. Keys are some information, right? So you can just use the protocol from before using claim or refund transactions, and you can perform this exchange. Again, with a guarantee that if the exchange goes bad, then the other person gets some compensation. Right? So this is kind of a little bit weird, because usually the encrypted information is what goes out publicly, and then the keys are kept private. Right? But here the encrypted information is what is kept local, and the keys go public. But these are like one-time keys, so this is totally fine. Right? So you still get privacy. Right? The encrypted information is kept local. The keys are going public. This is kind of reverse from what happens usually, but you still get privacy. Actually,
so if one of the parties is malicious, though, they might publish the encrypted data, right?
Yeah. So that is at that level you cannot guarantee anything, right? So even in this exchange, after the exchange, they can always release the information. right? So we are not worried about that aspect of privacy. What we want is if the honest party wants some, maybe both parties care about privacy, right? Maybe both of them are honest, and they're just worrying a little bit that maybe the other person is going to cheat during the exchange, and they want to use Bitcoin. But then if you use this protocol, then all their information is going to go public on the blockchain, right? Whereas if you use this, then they get to keep their information local. Only the keys go public. And then if they are like super malicious and they want to like release the information public, then they could always do that. Yeah, that's not something we prevent. But anyway, so the encrypted information is kept local. The keys go public, but it still gives you privacy. Actually, we hit like two birds in one stone. We also get like scalability, because instead of exchanging these like huge pieces of information on the blockchain, we are only exchanging 128-bit keys. Right? So this also gives you, so secure computation not only gives you privacy, but also gives you scalability here.
And what about the two new conditions that you have generated? Those are simple conditions?
Yeah, so you can think of this as, so these are 128-bit keys. The condition is just like a hash on the keys. So this key is legit if, so this condition phi k, red phi k, will contain the hash of the red key. And if Bob changed this key to a key prime, then it will not satisfy the hash. At that level, that is the level of condition checking that you want. So again, that's a good point. So here the condition was checking some information. If this information was large and the condition was large, it's like terrible. But here you're basically checking only a hash of a 128-bit key, which is totally reasonable. This is something that's supported in Bitcoin today. So secure computation gives you both privacy as well as scalability in this for information exchange. So far we saw this like information exchange. Let's look at something which is more general, right? So here I'm going to use this use poker as an example, and poker turns out to be a pretty good example because it involves a mix of everything, like some information computation, money exchanges of everything. Players start with their secret cards, which is like some kind of secret information. Then they have their own player strategies. They're going to do some computation according to the game. And then at the end of the game, someone is going to, they're playing the game so that one of them wins, right? So there is some money automatically involved, right? So poker is a very good example of a general contract. And maybe you don't care about poker. I don't care about poker. But poker is a billion-dollar industry. And insider attacks happen all the time. And there are sometimes casinos just like run away with all the money, all the players' deposits. These all kinds of things happen in the poker case. And if we have a self-enforcing contract for poker, that would be like pretty cool. Right? So, but here this is like more difficult than just the plain information exchange that we saw before, in at least like three different respects. So the first thing is that a poker game consists of like multiple moves, not like one swap of information, but it's multiple swaps, multiple rounds of betting and cards revealing and so on and so forth. And we need to penalize aborts after every move. Maybe the player aborts right after the first thing when he sees his cards and he doesn't like it, he's just aborting. You still have to, compensate the honest party, right? Because it's an unfair game. Right? And the second thing is, who deals the cards? Because you don't have any trusted party. We want to get like a self-enforcing contract for poker. And you cannot just let any party deal the cards because, it will deal the best cards for itself. Right? And the third thing is we still need to add payout to the winners. This is something that was not there in the information exchange, but here we want the winners to get the payout or at least get the compensation if the other person aborted somewhere in the middle. Right? So let's look at, let's start with like multiple moves, how to design multiple move contracts. So let's set some things up for in terms of like notation. So here Alice and Bob want to play like a multiple move game. Okay, they are basically exchanging multiple messages. So Alice sends M1, Bob sends M2, and so on and so forth. And the key thing here is that MI might depend upon the previous thing. So think about this as a poker game. Your move depends upon the previous moves in the game. Right? It's not something that you knew up front. It's something that you generate depending on how the game proceeds. And then you can have each of these messages or moves. You can think of it as satisfying some kind of condition, because these are conditions which enforce that the game is played according to the rules of poker or something like that. Right? So let's look at how we would design this multiple move exchange, and this is how the exchange looks. So the deposits are made one by one, and you have these conditions. So the conditions phi4 basically checks for all 4 messages. Phi3 checks. You can think of this like extension of the double lock. So there you had phi1, which just checks Alice's message. Phi2 checks both Alice's and Bob's first messages, and then this checks Alice, Bob, Alice. So it checks 3 messages and so on and so forth. You can also see that the amount of money varies a little bit, right? So for the first move is just one Bitcoin. For the second move is 2, and third move 2, and so on 2, 2, 2, 2, 2 until like the end, which is just 1 Bitcoin. So let's just go through like an honest execution, how people would play like a multiple move game. So the deposits are made from the top, but the claims will be made in reverse. So this is how the claims will happen. So first, so Alice claims M1. Then using M1, Bob can generate M2 and claim her money and so on and so forth. So you can see that at the end of the game, Alice gets 3 coins from Bob, and Bob gets 3 coins from Alice. So in an honest execution, nobody loses money. The money exchanges, Alice's coins are now with Bob, but Bob's coins are now with Alice. So this is good. But let's see what happens when there are robots in this protocol, right? That is the whole point of having coins in this mix. So let's look at what happens if there is an abort, and what we want to do is we want to penalize aborts after every move. Right? So let's look at like a sample scenario where let's say the first 2 messages happen, and then now Alice, for some reason, maybe she's not winning the game, she just wants to stop the protocol there. So she does not want to send the message M3, she just wants to stop the protocol. So once she does that, then we can see that these transactions are going to be refunded back. Right? So in effect what has happened is Alice gets 2 coins, whereas Bob gets 4. Right? So they started out with 3 each, but then now Bob gets 4 of the 6 coins, and Alice gets 2. So in some sense, basically Bob gets compensated with Alice's money. Right? So this is how you would design a multiple move exchange here. So you basically penalize every abort. So I just showed you an example of where an abort happens at the 3rd stage, but you can generalize this to any stage. Right? So now we have taken care of the multiple move exchanges. So let's look at the other problem, which is basically like who deals the cards. And the problem here is you cannot just let any party deal the cards. But let's just do this thought experiment with the angel, right? So if you had an angel, then the angel would deal the cards. Then you do some betting. Then the angel reveals more cards. You do some more betting. Reveal new cards according to the poker games, and then you do more betting, and so on and so forth. So everything is great, but this actually sets things up because we already saw that secure computation implements angel. So you can just get rid of the angel and then use protocol messages. So in effect, you have the secure computation protocol, which reveals players' cards. This actually goes back to the classic, playing mental poker, where they use secure computation, kind of some variant of secure computation to implement this angel. Right? But then we still have to deal with this. Secure computation replaces the angel, but it does not guarantee fairness. Right? So players can still abort after, during the secure computation, or right after the secure computation, right after Bob gets his cards and he doesn't like them, he can abort. Or he can abort at the very end when he knows for sure that he's not going to win, he can abort. Right? So secure computation does not do anything about that. But then we saw this multiple move exchanges, right? And we are going to apply that contract on top of this game. So what we are basically going to do is basically looking at this protocol as having 2 types of moves. Basically, one is secure computation moves. These are the red messages, and one is betting moves, where you just ask the players to sign their bets. Right? And then both have some conditions checking the validity of these messages. So you have the secure computation protocol as well as the bets. The bets have to be made according to the poker rules. So you still have some. So these moves specify some conditions on how the entire protocol should move, and then you have this multiple move exchanges on top of these conditions, and then you can ensure that you play a game of poker. If someone aborts, then the honest party still gets compensated. Right? So what we have seen so far is that either the honest party gets compensated, or the poker game is completed until its very end. Right? And what we need to do is basically adding the payout to the winner. The winner needs to get the money, right? So you play the game, you exchange some moves. At the end of the game, there is some winner, and then the winner should get the moves. And the way you do it is basically have some conditions on the messages, which says that the blue condition equals 1 on the entire transcript of the protocol. It's 1 if and only if Alice wins, and the red condition checks if Bob wins. and then you just add like a couple of transactions at the beginning, then you're good. So you do all, you play the game until here. At this point, you are ensured that either the honest party gets compensated or the poker game is completed. And then after that, the winner can take like 1 Bitcoin. So here I'm assuming that the payout is 1 Bitcoin. Right? So what we have at the end of the day is basically a poker game where you don't have to trust any third party. There's no online casino or dealers that you trust. You just use a secure computation protocol. But it also takes care of the fairness issues. You have like guaranteed payout to the honest party or compensation. And in the poker game, you can set the compensation equal to the maximum value of the payout. So you have a fully self-enforcing contract. Either the winner wins the pot, or it gets a compensation which equals the pot. So it's good either way.
I missed the betting part of the payout to the winner.
Mm-hmm.
So those conditions depend on the sequence of.
Yes, so the condition depends on the entire transcript. Actually, each of these messages, like phi 2 depends on both the first 2 messages. Phi m depends on the first m messages. And the last winning condition depends on all m messages. Yeah. So the condition is still checking like a lot of information. It's checking the entire poker.
So that happens just at the end of the game.
Yeah. So the deposits, so people put up their deposits upfront because they know these conditions ahead of time, right? And then when you are claiming it, you can claim it only if you win. So out of the top 2, only one of them is going to get claimed. The other one will get refunded. Right? So that's how the winner gets the payout. So yeah, so this is what you can do. Right? Yeah.
Does the amount of money that each player deposits as insurance depend on the amount of bets that they might do? Is there a pattern there?
Yeah, there's a pattern. So here the compensation equals 1 Bitcoin. The payout is also 1 Bitcoin. Right? So it depends on you can vary these things. It's relatively flexible, but ideally what you want is if someone cheats, then the other one should get the money as if he won the game. Right? So that's what you want. So you can just set the 2 equal, and there you go. So you get like a pretty good self-enforcing poker contract. So the idea that we saw with poker, about like using a secure computation protocol and then putting like a multiple move contract on top of it, it's fairly general. You can, you don't have to do the secure computation for just the game of poker. You could do the secure computation protocol for any function f, right? So what you actually get is basically starting with these claim or refund transactions and use secure computation. You get like smart contracts, and you can make them privacy preserving, using secure computation we saw before. Right. So far I've shown you this privacy preserving aspect. Let me talk about like scalability. Okay. So we already saw something about like scalability between how we actually reduce this information to information exchange to just a key to key exchange. So this information could be several megabytes, but then the key is just like 128 bits. Right. And here I want to make this distinction between the on-chain complexity and the off-chain complexity. So what I mean by off-chain complexity is basically the secure computation part, something that's done locally. It does not go on the blockchain at all. It's just done locally between the 2 parties. Nobody else has to see it. Right? So that is off-chain, and for the next few slides, we will assume that this is cheap. This is local computation. Right? Nobody else, the Bitcoin network does not need to see it, the escrow does not need to see it, they don't need to participate on it. So we'll call it cheap for the time being. And this exchange is what goes on the blockchain. And this is what we call as the on-chain complexity. Here, you probably have to pay a transaction fee for every claim or refund transaction, and the entire network may have to verify it if it's going on the blockchain. Right? So what we want to minimize is basically we want to minimize on-chain complexity, and we don't so much care about off-chain complexity, at least for the next few slides. Okay. And what we saw before was basically kind of like making the on-chain complexity independent of the size of the information. You just exchange keys. You don't care about like how big the information is. That is all handled inside the secure computation part. Right? So this is scalability with respect to the size of the information. Let's look at scalability with respect to like other dimensions. So far we have seen only like 2-party exchanges. Let's look at like a multi-party exchange where a set of n parties, they want to perform an n-way exchange. Okay. And then the problem becomes like much worse here because all of them might collude against one party. Right? So in this case, when all of them collude against one, what you need to kind of ensure is that if anybody aborts, then you kind of need to compensate everybody because you don't know who is the honest party. Right? So if someone aborts, then you want to compensate everybody. And what we saw until now is basically these claim or refund transactions, but these were just 2-party transactions. Right? So they were not multi-party. They were just between Alice and Bob, someone setting up some condition and putting some money, and it was a two-party simple transaction, but this was only like two parties. And now we are in a multi-party setting, and the question is, well, can we implement this n-way exchange where you want to be resistant to all kinds of collusions against one party? Can we implement this using just claim or refund transactions? These are simple two-party exchanges. Can we do n-way exchanges from two-party exchanges? Right? And here my work shows that you can actually do multi-party exchanges using claim or refund transactions. So this is actually how the transaction graph looks like. It looks a bit weird because there are arrows going both ways from these parties. I just want to say that the mechanism is much more complex, and each of these arrows are checking for different information. The arrows also carry like different amounts of money, just to make sure that if all of them collude against one, you still want to ensure that the honest party gets compensated. So the mechanism is more complicated, but it can be done just using your simple two-party transactions. So we are boosting simple two-party transactions to complex multi-party transactions. So that's the way to think of it. So this is the multi-party case, but you could think of like a different scalability dimension. Let's say scalability with respect to like multiple exchanges. Maybe a set of parties performed an exchange, they like it, they want to perform one more exchange, they want to perform like 1 million more exchanges. The problem with this is that you need to make on-chain transactions for every exchange, because for every time you make this exchange, the conditions are different. Right? The conditions depend on the information that is being exchanged. In different transactions, even involving the same parties, different contracts are going to have like exchanges of different information. So the conditions are going to change. So do you need like on-chain transactions for every exchange, or can we do like something slightly clever? Can we do like just make one set of transactions on the blockchain and somehow use it for multiple exchanges? So what I mean by this is, you put one set of transactions on the blockchain, do exchanges locally. If the exchange is good, great, you go to the next exchange, do it locally. If that is also good, keep going. But somewhere down the line, maybe the 10,000th exchange, something goes wrong, then you can always go and appeal to the blockchain and get your compensation. So that is kind of what I want here. Right? So we make only one set of transactions. Even though the conditions on the transaction depend on the information exchange, we want to somehow bypass that. Maybe put some kind of like some universal condition up front, and then make all these exchanges local. Something goes bad, then you go and take your compensation. That's what we want. And here my work shows that you can actually do these exactly what I told before. So you can do an unbounded number of exchanges using just a single set of claim or refund transactions. Again, here secure computation is going to be very important to set things up, in setting these universal conditions up front, so that nobody can cheat. Right. So let's look at like another dimension of scalability. So here I want to look at in terms of yes.
In this case, do you want that you should know what all parties are going to participate?
Exactly.
Yeah.
Exactly. So it's the same set of parties. They're going to run a secure computation up front. They're going to generate some kind of like master secret keys, master public keys to set these like claim or refund transactions, and then they go ahead and do. But it's still like exchanges between the same set of parties. So the next slide we'll talk about exchanges between multiple parties. So here we are talking about like infrastructures for contracts. There are many parties in the universe, and maybe all of them want to perform exchanges, like let's say pairwise exchanges. Yeah, ideally, what you want to do, or what happens in today's world when a lot of people want to do exchanges, they don't even know whom they're going to exchange with. Well, you have like some kind of a client-server architecture, right? So clients put up what they want to exchange, or what things they're looking for, and then the server does the matchmaking. You go and search for what information you want, and then the server gives you a listing, and then you choose to do the exchange. Right? And then there you can use the three-party exchange. Three-party exchange, you can use it here to facilitate exchange between Alice and Bob, and you use it with the server, but then you don't have to trust the server. And in particular, the server can collude with Bob against Alice, but still you're fine. Alice will be ensured that either the exchange happens or she gets some kind of compensation. Right? But this is still bad in the sense that the total number of transactions now grows quadratically with the number of parties, because if you look in this diagram, there is still an arrow between Alice and Bob. Right? So if Alice wants to perform an exchange with Carol, then there has to be an arrow between like Carol and Alice. Right? For any pair of parties, you'll need a claim or refund transaction going between them. Right? So this is still bad. The total number of transactions is going to go quadratic in the number of parties in the universe. So can we do better? And here I want to take you back to this like 4-party diagram that we saw before. So if you look in this diagram like slightly closely, then you see that there is no arrow between Alice and Bob. Right? So in the general multi-party case, the number of transactions is actually linear. So this in particular means that not all pairs of parties are involved in claim or refund transactions. What this means is that you can call Carol and Dave as the server. So everybody makes transactions with the server as if they are playing in a four-party game, where they don't need to know, because Alice is not making a claim or refund transaction to Bob. She does not even need to know who Bob is. Right? And still you don't trust the server, because this is a four-party mechanism which is resistant to collusions of up to three parties. So the server can collude with Bob against Alice and still you're fine. Alice is ensured a fair exchange in the sense that either the exchange happens or she gets compensated. Right? So what you have is a client-server architecture with like linear number of on-chain transactions. Yeah?
So does, during the actual exchange, is that up to them?
Yeah, so just before the actual exchange, they have to perform some secure computation involving the server as well. But the claim or refund transaction itself, you don't need it. Plus, on top of this, you can think of this as like using the scheme from before, where you can make a set of transactions and do unbounded number of exchanges, so you can amortize at that level. So everybody registers with the server, makes some claim or refund transactions with the server, and then they amortize over like multiple exchanges involving different parties. And you still have only like linear number of on-chain transactions among parties in the universe, as opposed to quadratic. Quadratic you can easily do using the results from before. For linear, you have to use this like slightly more complicated scheme. So what we have shown is basically, starting from these claim or refund transactions, the simple transactions, two-party transactions, but then using secure computation, you can boost them to like smart contracts which are scalable as well as privacy preserving. So this is what I've showed you so far, and we've discussed like scalability issues with respect to on-chain complexity. Let's go and look a little bit more into like the off-chain complexity, which is basically secure computation. We were using secure computation left, right, and center in all of the schemes. But how practical is secure computation? Right? Is secure computation something that can run today, or is it not? So here I want to say that secure computation is like a major area of research in cryptography, especially in the last decade. There have been like tons and tons of papers improving the efficiency of secure computation. And in this regard, I've done work in improving the asymptotic complexity in terms of like reducing the dependence on the size of the function, let's say, and also concrete efficiency, where I mean by a factor 5x improvement, a factor 10x improvement, stuff like that, both in the two-party as well as in the multi-party setting. I've also worked on designing more efficient building blocks for secure computation, like oblivious transfer or cryptographic commitments. And obviously, the more efficient your building blocks are, the more efficient your secure computation protocol is. I've also done some work on studying the cryptographic assumptions for some of the practical secure computation techniques like free XOR. So overall, what I want to say is secure computation is something that's is definitely moving from theory to practice. And for some of the applications, for example, the poker application, the function is not that large. Every game of poker is going to be like, I don't know, maximum 15 rounds. And it's a very small function. Those things, for those things, secure computation is definitely practical. If you're talking about like real-time secure computation, that's still a bit out there, and we don't know still how to do it. But for some very simple functions, it's totally doable. And actually, secure computation was my main area of research until I started working in like smart contracts. And the reason why I started looking at smart contracts, basically, secure computation, gives you the best possible privacy, but does not give you fairness. It does not prevent this cheating strategy, and cannot prevent because there's an impossibility result, right? But just because there's an impossibility result doesn't mean this is not a cheating strategy, and you still have to do something about it. In the real world, this is a cheating strategy. Just get the output and stop the computation. And I was looking at smart contracts in this way. So maybe if you have a fairness problem, then you want to penalize the cheating party, and you want to compensate the honest party. And this is somehow like a very good relaxation for getting fair secure computation. But why stop with just like penalizing bots? Secure computation involves like a lot of expensive cryptography to prevent cheating. They use zero-knowledge proofs or cut-and-choose mechanisms, and this all adds to the cost of secure computation. But maybe we can do something better, right? Why penalize only bots? Maybe I can penalize like general cheating. So maybe the adversary cheats in a specific way, then he will have to pay some huge penalty. And actually, we were able to translate this idea and get like better, more efficient secure computation protocols using this idea. I don't know if you know about the dual execution protocol, where a bit leaks, and then where one bit leaks, but then the leaked bit you can detect if the bit is leaked. this result basically so 1-bit leakage is great because if you're having a large data and 1 bit is leaked, it's not a big deal. But when you're doing like multiple executions of that, when you're doing like billions of executions, you basically leak the entire data. And what this result does is that we still allow 1-bit leakage, but then if the leakage is detected, then we'll impose a huge penalty on the cheating party. So you can try to cheat multiple times, but then one of the times you're going to end up paying a huge penalty. It's just not just caught, but you also end up paying a huge penalty. And we still do it while keeping like the dual execution cost the same in the optimistic setting. So that is this result. Also inspired by the infrastructures for smart contracts, we also looked at scalable infrastructures for secure computation itself, where you can imagine like a network where some parties have done some pre-processing and they have set up, performed some expensive pre-processing, and other parties they still haven't set up expensive pre-processing. So can they use the rest of the network to do something else? So this you can think of like BGW for t greater than n over 2, like where the infrastructure is like some oblivious transfer pre-processing. So it's that kind of result, and this was again inspired by the infrastructures question for smart contracts. So so far I've talked about like information to information exchange, information to money, but let's look at like other parts of this diagram. Let's talk about like computation to money exchange. Okay, and this is something that happens all the time. It's basically cloud computing or outsourcing, right? So the client wants some computation to be performed. The cloud is performing the computation in exchange for some money, right? But let's consider a setting where either party could be malicious. Maybe the client pays upfront, but then the server doesn't compute at all. Or the server computes first, but then the client never pays, right? So again, you have like some kind of you need an atomic exchange of computation for money. It's like a chicken and egg problem. But we were solving chicken and egg problems before with information exchange, right? And here we actually have a result which shows that you can make these exchanges atomic. Again, we'll just use the claim or refund transactions that we saw before. It involves like using verifiable computation schemes and also some secure computation to bootstrap things, and you can still do this. But this was still a setting where you have a single client and a single server. What happens if a client wants to outsource the computation to a large network? And here our question is actually motivated by Bitcoin itself. If you think of Bitcoin, at some very kind of like a deep level, there is an exchange of computation for money happening. So Bitcoin mining, they're doing all these like proofs of work. There's a lot of computation. In exchange, they get some rewards from the Bitcoin system, right? So they do this mining, and then they get some Bitcoin return. So in some sense, that's a swap of computation for money. But this proof of work and all the computations that's being done by the miners is totally useless outside Bitcoin. It's actually like a tremendous stress on the environment, right? It's a lot of computational energy doing nothing outside Bitcoin. And it would be great if you can, match this up with this. So a client wants to outsource some useful computation, maybe give it to the miners, and maybe also, have the miners perform useful computation and at the same time maintain a currency system. Can we do this, right? So here it needs like a deeper understanding of how consensus mechanism in Bitcoin actually works and how crucial is Bitcoin mining to this process. So it's actually a new security model for consensus itself. Bitcoin itself provides a new security model. And in this area, I have done some work in designing like broadcast protocols in new security models, like models where the public key infrastructure could be compromised, and you still need to solve Byzantine agreement. But this is like this is a very different problem. It's a dynamic setting. Parties are coming in and going out. Not everybody is connected to everybody else. So it's a much harder setting. But if we can combine these two things, that would be a dream goal. So moving on to like more general contracts which involve all of them. So we actually saw this example of monthly installments where like a key unlocks a car if and only if the monthly installment is paid. And in all the protocols that I've showed you before, parties put a security deposit up front before they start the protocol. But in this monthly installment setting, I mean, the whole point of using monthly installment is that they don't have the security deposit up front. Right? So this is like a very different problem. Right? And also you can think of like simple interest where the money keeps growing over time. Or you can go on to like more like Wall Street stuff like stocks, bonds, options, like all kinds of like very complex financial instruments. Like the protocols that I showed you do not really solve this, and we need like new ideas here. So this is something that I consider as like very exciting work. And also in the other direction, if you look at like exchanges that happen today in the world, think about like Amazon, you're getting like physical objects for money, Right? So there's exchange of objects and money, sometimes like objects for objects, like on eBay. And here we want to like how do you even like use the ideas that I showed you before? Like how do you construct this like condition phi? What is an authentic object? Right? So there's been some work on like computations on objects itself. So I don't know if you might have heard about this more famous work by Boaz Barak on computing on like nuclear warhead missiles, just to make sure that everybody is diffusing the correct nuclear warhead. So there's been some work, but there's a lot more to be done. And also, how do you capture value of objects? If you want to set up like a security deposit or a penalty, you need to set up that value depending on the value of the object, or even like value of information. How do you capture value of information? What is the value of information? It's time dependent, and also sometimes just putting like some value on the information itself might leak some information about the secret information. So there are all kinds of like more complex stuff here. Right. But this is something that I want to do, want to explore in the future. So that's it. Thank you. Sorry for going over time.
No. Any other questions?
I have one more. So, you talked about multi-party exchanges.
Right.
But can you do the general contracts with multi-party? Like, could you do the poker contract in a multi-party setting?
Yeah. So again, now the messages. Yeah, I didn't show all those like multiple move contracts. It becomes like much more complex in the multi-party setting, especially when you have to be resistant with collusions. But the secure multi-party computation protocol still exists. It doesn't give you fairness, but it still exists, right? Against like collusions of up to n-1 out of the n parties. So it's still being messages according to the secure computation protocols being exchanged. There are bets being exchanged, and then you can apply a multi-party contract, which I did not show, but you can apply a multi-party contract on that, and you can still run this protocol in a way such that either the protocol completes, the poker game is fully executed, or if someone aborts in the middle, it could just be one party aborting in the middle, then everybody else gets compensated.
But doesn't poker have like a condition that you shouldn't show your cards to other players?
Yeah.
So
Show your cards in what's this way. It depends, right?
So
Sometimes
if-
when you're winning,
if you're playing, if you and I are playing, and I'm malicious, and I have 4 people at the table, and you're only one person.
yeah. So that is
Most
like
people share their cards.
yeah, so
but
that is-
otherwise they play honestly, I think.
right. So it depends. So if the issue that you're hinting at is basically collusions, right? So there are 5 parties, but 4 parties that actually are communicating out of band.
Yeah.
And then they basically share all their cards, and then it's really unreasonable for the honest party. So secure computation in general like does not solve the collusion problem at that level, where out of band communication is. When you start with an input, but if you have like additional information, then secure computation does not guarantee anything. But with the 2-party poker, you don't have to worry about collusion because there are only 2 parties. What does out of band communication even mean? In the multi-party case, and when you want to design something which is collusion resistant, you need more. You need other kinds of ideas here. Yeah.
So I guess there's a class of contracts that have this problem, right?
Right. Yeah. So out of band communication. So you can use. So that's definitely an open question, and you can use like some of the ideas which I showed. Like you can have. So you can have like a central server. But this is not like your regular online casino which deals the cards, etc. It's there only for like facilitating the exchange, but it also can keep track of players' transcripts from like different games, and then maybe it can, you'll need like more cryptographic magic stuff for the server to perform like some kind of statistics on the poker game so far, which is basically what your online casino also does in order to prevent collusions, right? They keep track of who's playing at what times, who is playing with like other pairs of parties, and whether they're cheating. There's some kind of statistics algorithm that they run in the background. And you could go to such a model if you use the client server infrastructure that I showed you before, where the server it's there in the exchange just to facilitate it. It's not going to deal the cards, it's not going to do anything. It's just going to make sure that the game of poker is played properly. But at the same time, it also has access to the transcripts. At some level, you still need more cryptographic, like homomorphic encryption type style stuff to perform under the encryption without the server learning what the cards are. But yeah, that's definitely something which is open. It's a great question, great research question for the future. Yeah, thanks.
Any other questions?
Yeah.
You talked very briefly about Ethereum, right?
Yeah.
It is a new kind of digital currency, and I think they provide facility for doing smart contracts.
Yeah.
But
So
they don't have any privacy preserving.
So, yeah. So it's a very interesting comparison between like Ethereum and the stuff that I showed you here. So in Ethereum, you program your smart contracts, like the full contract, you just program it and put it on the blockchain, right? And when you need to enforce this contract, everybody in the network has to enforce this contract, right? So all the computations. So it does not operate at the claim or refund transactions level. It operates at a much more macro level where everybody. So the burden on the blockchain is huge. You put like all. So Ethereum provides like a programming language for scripting any kind of contract. So you put your program up in the blockchain. And when someone needs to like change the state of the contract, then they post a message to the blockchain, and all the miners are going to upgrade the state of the contract. So in effect, the bad part is basically is that like everybody on the network needs to do the contract work.
So it's not a contract between two people?
It's a contract between two people, but the contract is going on the blockchain. As a result, everybody is performing the computation. So this is the scalability issue, right? So again, when you need to check whether the information matches the condition, the miners are doing this work, right? And there we want to like reduce this dependence on the information. We just want to check a key against a hash as opposed to like a big chunk of information with a condition, right? So in Ethereum, like everything is very complicated, and it's at the level of like huge pieces of information interacting with each other. But Ethereum.
No privacy.
Yeah, plus there is no privacy. You can add some cryptography to get some privacy and maybe use zero-knowledge proofs or snags, but still you don't get the great scalability issues, great scalability benefits that you get by using some off-chain computation. So the key idea that I showed you here is using secure computation as an off-chain. Do most of the heavy lifting off the chain. Use only like the key-to-key exchanges on the chain or something like much simpler, so that you get like better scalability. Also, once you start working with like claim or refund transactions, you can also amortize across different exchanges. Such things are not possible in Ethereum if you just hard code your entire contract. But the cool thing about what I said here is basically you can implement claim or refund transactions in Ethereum and still have all the protocols that I showed you here, right? So Ethereum supports all kinds of contracts, but it also supports claim or refund transactions. Just use claim or refund transactions, use all the protocols that I showed you here. That's like one answer to the scalability issues that Ethereum will probably face in the future. Yeah. Cool. Thank you. Thanks.